Okay, section 3.7, graphs of rational functions. We're going to talk about all the different parts of graphs of rational functions. We're going to pull from what we've already learned dealing with discontinuities, specifically infinite discontinuities, because that leads us into one of the terms we're going to talk about today. Point discontinuity is also something we'll see again today that we've talked about before. And also another concept we've talked about is going to explain another term that we have today. End behavior is going to explain what's called a horizontal asymptote. So let's get into some of the vocabulary of this section. First, what exactly is a rational function? A rational function is a quotient of two polynomial functions. A polynomial function would be like a linear function, a quadratic, a cubic, and so forth. Okay, we have one divided by another. The trick with that is that it's always going to be a fraction. That's what rational means. So you're always going to have some type of discontinuity, because discontinuities are caused by zeros on the bottom of a fraction. Okay, so we see here h of x not equal to 0. An asymptote. An asymptote is a line that a graph approaches but never intersects. So this is what our graph's going to be approaching, and these are caused by these issues here with 0 on the bottom, okay, and also by by end behavior. It's going to tell us how the graph's going to act at the end. Vertical asymptote. These occur where f of x is undefined. In other words, where the bottom of the fraction is equal to 0. So when we're talking about a discontinuity, if we will get zeros, the zeros on the bottom, or anything that causes 0 on the bottom, will tell us a type of discontinuity. Okay? If it does not cancel out, in other words, the factor that caused the 0 on the bottom does not cancel out, then we call that an infinite discontinuity. In other words, the graph breaks at the infinities. A vertical asymptote explains that break. Okay? Vertical asymptote is the imaginary line, okay, a line that a graph approaches but never actually touches. That's what is occurring at that infinite discontinuity. Now, a horizontal asymptote is the line y equals b. B is a number, so it could be like 3, 2, any number, -7. For a function, f of x, if f of x approaches that number as x approaches positive infinity or as x approaches negative infinity. Okay, as I said before, we talked about end behavior. So what's happening to y as x goes way right? That would be the first one, the limit of f of x as x approaches positive infinity. What's happening to y when x goes way left? Well, the horizontal asymptote tells us that it approaches a number. To find that, we simply have to look at the highest exponent on top and the highest exponent on the bottom and compare them. Depending on how they compare, will tell us whether we have a horizontal asymptote or not and what it will be. It'll tell us how the end of the graph, real far left and real far right, will actually, what that will happen at that point. So there are three different situations where it could cause a horizontal asymptote. Okay, first, if the degree of the top is smaller than the degree of the bottom. What's the degree? The degree is the highest exponent. So if the highest exponent on top is smaller than the highest exponent on the bottom, then you will automatically have, no questions asked, a horizontal asymptote at y equals 0. It is automatic. This is your horizontal asymptote. In other words, way left and way right, the graph will approach the line y equals 0. The end behavior, the limit of f of x, which I can rewrite again, as x approaches negative infinity will be 0, and the limit of f of x as x approaches positive infinity will be 0. So the ends will approach that 0 if the degree on top is smaller. That's the first case. What if they're equal? That's case number 2. If the degree on top is equal to the degree of the bottom, then there is a horizontal asymptote, and it is established by y equal to the leading coefficient of the top, which is a number, divided by the leading coefficient of the bottom, also a number. Okay? A coefficient is the number in front of the variable. A leading coefficient is the number in front of the variable that has the highest exponent. So when you're comparing your exponents, look at the number out in front. If they're equal, the numbers in front will tell you where your horizontal asymptote will be. It will be some number other than 0. It could be 3, 2, negative 7. It could be any of those. We do that by dividing the two numbers. The third situation, if the degree on top is larger, if it's bigger. The highest exponent on top is bigger than the bottom, then there is no horizontal asymptote. So the first two cases tell us the horizontal asymptote will be 0. The horizontal asymptote will be y equal to some number. The third case says it doesn't exist. There isn't one. What will replace it? An end behavior asymptote will exist instead. Now, an end behavior asymptote could be anything at all. It could be a line, it could be a parabola, it could be a cubic, a quartic. Some polynomial is what it will be. Okay, we find that by actually dividing out the polynomials using long division. And in some special cases, we could use synthetic. But in most cases, we'll be using long division. We'll probably, instead of studying all end behavior asymptotes, focus on a very specific one, okay, and that's called a slant asymptote, which we'll get to here later on after we get through a couple examples. Okay, so horizontal asymptotes tell you about how the graph will behave at the ends. Degree on top is smaller, it's y equals 0. If they're equal, you go to the numbers in front, y equal to some number. If it's bigger on top, then it will actually approach some other function, whatever the result is. Okay? Let's start out simple. You got through all that, the big vocabulary, lots of writing. Let's put it to use here. Determine the asymptotes for this very simple function, f of x equals 1 over x. Then graph f of x. Okay, this is a graph that really should be imprinted into your head. Okay, this is one you should have memorized, 1 over x. If you don't, we're going to see it real fast. To determine the asymptotes, the first thing I want you to talk about is discontinuity. Okay? Discontinuity is caused by zeros in the bottom of a fraction. So what will cause a 0 in the bottom of this function, 1 over x? The answer is 0. If we plug 0 in, we will get a 0 on the bottom. There is no other number we can plug in to make it 0 on the bottom. Okay? Question number 2. The x that caused this 0 in the bottom, will it cancel out with something on top? In other words, we might have a function that could be factored, and we might actually be able to cancel out the x. But we didn't have that to begin with. So does the x cancel out? In this case, the answer is no. It does not cancel out. If it does not cancel out, then this causes an infinite discontinuity at x equals 0. If it canceled, If there was an x on top and it was able to cancel out, then that would be a point discontinuity. It would cause a hole in the graph. Okay? So let's first determine discontinuities. The discontinuities will now start telling us about asymptotes, because wherever an infinite discontinuity occurs is where a vertical asymptote will occur. These go hand in hand. Okay? If you have an infinite discontinuity, you have a vertical asymptote. Vertical asymptote. It's a vertical line that the graph will approach but never touch. Keep that in mind when we go to graph this. Okay. The other asymptote that we have to be concerned about is the horizontal asymptote. That is established by looking at the degrees or the highest exponent of the top and bottom. Now, considering we have no variable on top, okay, I don't see one, okay, that means that that has an exponent of 0. So if you don't see a variable, the highest exponent is a 0. So the top's exponent is a 0. The bottom is an understood 1. Let me do that in a different color. 1. So we have 0 over 1. Is the top bigger, smaller, or the same? The answer is it's smaller. 0 is smaller than 1. So we automatically have a horizontal asymptote of y equals 0. Automatically. So we've determined the asymptotes. Let's attempt to graph the function now. Okay, we have a vertical asymptote. Again, a vertical line that is not part of the graph. Okay? Imaginary, if you want to say that. Okay? You don't see it as part of the graph. Okay, that the graph will approach. So that's the vertical asymptote at x equals 0. Horizontal at y equals 0. Another imaginary line that the graph will never actually touch. So where's the graph at? Well, we can establish that by just plugging in some numbers. So let's start at, say, 1. So if we plug 1 into the original, okay, again, the original is y equals 1 over x. Well, 1 would be 1 over 1. So when we plug in 1 for x, we get 1 for y. So we get the point 1, 1. All right, now, there has to be more graph up here in quadrant 1. Remember that the graph must approach the asymptotes. It will get closer and closer and closer, but never actually touch. So I'm going to draw this going towards the asymptote, but it will have to bend, okay, because it will never, ever, 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 ever get to touch it. It gets closer and closer and closer and closer and closer, but never touches. Same with the horizontal. It will get closer and closer and closer, but it must bend. It cannot touch. So there's the first part of the graph. If we plug in a negative 1, 1 over negative 1 would be negative 1. So we get negative 1, negative 1. Again, the graph must get closer and closer and closer, but never actually touch our asymptotes. So there's the graph. If you want to plug in more points to confirm that, you can. Also, what we can do is we can put it in the calculator. So let's go ahead and graph it. 1 divided by x. Start with a zoom 6, and there it is. We can confirm our points, calculate the value at 1. If you wanted to get more points, plug in 2, you get a half, and so forth. Okay? But that's the graph, exactly as we just drew it. can trace. You can see the graph will get closer and closer. Okay? Never actually touch. This keeps getting, I know it looks like it's on the axis if we zoomed in though, or if you look at the y value here, okay, you can clearly see it's not touching the y-axis. It is, I'm sorry, the x-axis is it's at y equals 0.1, so it's off of the x-axis, getting closer and closer and closer, but never touching. Okay, so that's a little taste of asymptotes. Vertical, horizontal. Let's take a look at another example. Again, we want to figure out where the asymptotes are and then graph the function. We should always start with discontinuity. Where would the bottom be equal to 0? Because if we get a 0 on the bottom, that's a problem. So our function is 3x minus 1 over x minus 2. What value would give us 0 on the bottom? The answer is 2. Does the x minus 2 cancel with anything on top? No. So we can say there is an infinite discontinuity at x equals 2. Okay? Which tells us there is a vertical asymptote at x equals 2. So we've established an asymptote, vertical asymptote. We now have to figure out the horizontal asymptote. We need to look at the degree of the top versus the degree of the bottom. The highest exponent on top is 1. The highest exponent bottom is 1. So they're equal. That means we will have y equal to the leading coefficient of the top, the number in front of that variable that has the highest exponent, which is a 3, divided by the number out in front of the variable that has the highest exponent at the bottom, which is an understood 1. So our horizontal asymptote is y equal to 3. Okay, we've established the asymptotes. Let's try to graph it. We have a vertical at 2. We have a horizontal at 3. Again, we need to plug in a couple values into the function to figure out where the graph is. So the easiest one to plug in would be x equals 0. Okay, so if we plug in 0 into the original, okay, 3 times 0 is 0, so 0 minus 1, we have a negative 1 on top. We have 0 minus 2 and negative 2 on the bottom, so negative 1 over negative 2 is a half. So 0, 1 half would be a point. 0, 1 half is a point on the graph. The graph now must approach the asymptotes. It has to get closer and closer and closer to the horizontal. It has to get closer and closer and closer to the vertical. Never actually touching, but keep getting closer and closer and closer. All right, let's check an x value out here, say 3. Okay, what's happening at 3? Well, if we plug in 3 up here, we're getting 3 times 3, which is 9 minus 1, which is 8. And 3 minus 2 is 1, so 8 over 1 would be 8. So 3, 8 would be a point on the graph. Again, we can continue this asymptote. The graph must get closer and closer and closer, closer and closer and closer to the 2 asymptotes. Let's confirm. Okay, the original function is 3x minus 1, x minus 2. Oops. I forgot to divide. Okay, so 3x minus 1 divided by x minus 2. Notice that you have to put parentheses around the top and the bottom, or you won't get the right graph. Calculator needs to know what is on top and what's on the bottom of the fraction. Zoom 6. Okay, now my calculator is an older calculator.
Please excuse me.
As I was saying, my calculator is an older version. Okay, the newer calculators don't actually have this show up, but this vertical line, okay, you can see with my arrow, okay, on the calculator. This vertical line does not exist. It's not supposed to be there, okay? On a newer version of the graphing calculator, vertical asymptotes do not show up. On the older versions, they do. That is not supposed to be there. You shouldn't see the vertical asymptote. Okay? That's basically what it is, though. That is not part of the graph. We cannot trace that. Okay, you'll see it'll jump from the bottom and automatically go to the next one. I can't follow that line. Okay, it is not part of the graph. So you can see, though, that's where vertical asymptote is occurring at 2. We calculate the value at 2. There's nothing there. Notice there is no y equals. There's nothing there. Y equals nothing. And also the end behavior. If we change the window, let me make the x min and max larger, like 100. Negative 100 and 100. You can see the ends. Way out left, okay, as you can see with my cursor here, way left and way right is leveling out to, looks to be about 3. Well, algebraically, we said that right over here. Y equals 3. It's a horizontal asymptote. So we know that the graph is leveling out to a certain number. That's established by the horizontal asymptote. So that also tells us some things about the end behavior.